Let's now look at our x transformations then. So, original graph again, f of x equals x squared. And let's look at the first rule, f of x plus a. And we said that a equals 2, just for this example. So f of x plus 2. If you remember from our rules, which you need to learn, you must know your transformation rules. This is a translation by vector minus 2 in the x direction and 0, so nothing changes in the y direction. So let's draw the original. And after this transformation is made, the graph moves to the left by 2. So all the x coordinates has been moved to the left by 2. This is our new transformation now. And conversely, if we look at f of x minus a, so original f of x equals x squared, let's draw that, passes through the origin, and our new transformation f of x minus a, which again we said a is 2, so you need to write, this is a translation by vector 2, 0, so it moves to the right this time by 2 and nothing changes in the y-axis. So the origin here was where the minimum point was. The minimum point has now moved here, 2 to the right. That being said, let's move on to our third one, our third x transformation. So original was f of x equals x squared. Our new one is f of ax, and in here again we said a is 2, so we're looking at f of 2x. You remember from our description that this meant we had a scale factor of 1 over a, so 1 over 2 is our scale factor. It's a stretch parallel to the x-axis, so that means all x values will be times by a half. So here's our original, 0, and if I take this point 1, this goes up to y equals 1. After my transformation, however, all my x values have been times by a half, so actually x equals a half, my y equals 1. No change in the y, just the change in the x. So essentially, my graph has been compressed along the y-axis, and we can see that comparing it to my original, it gets squished in like that. Now you're probably thinking, oh well, that's exactly what happened with the y transformation when we had af of x. So let's compare af of x with f of ax. If we look at the sine graph, which goes between 1 and minus 1, you'll learn about this later in trigonometry. The sine graph goes like so. Degrees along the x-axis and proportion on the y-axis. So this is 180 degrees, this is 360 degrees, 540 degrees, and 720 degrees. If we apply this transformation here with a equals 2, so we have 2f of x, remember all the y coordinates get times by 2, so actually the graph goes between 2 and minus 2 in my new transformation. So everything is stretched upwards and downwards parallel to the y-axis, like so, you see, and the x coordinates have not changed at all. Now let's compare that to what happens with f of ax, so where a is 2, f of 2x. Let's draw the sine graph again, 1 to minus 1, like so, 180 degrees, 360 degrees, 540 degrees, and 720 degrees. So remember, the scale factor equals 1 over a, so that's 1 over 2. So that means all x coordinates are halved. So this will actually go like this. It will be compressed inwards, and I'll get double the amount of oscillations. So you see, actually, this is very different from 2 times f of x. The whole thing has been squished inwards, as opposed to when we had 2f of x, where everything was squished, well, elongated, up and down. And finally, the last transformation is the minus, is the f of minus x. So f of minus x. So remember, this is the same as when a equals minus 1. So before, for minus f of x, the graph flipped like so about the x-axis. This time the graph is going to flip about the y-axis. So again, my original f of x equals x squared, passes through the origin. This is going to be flipped that way and that way for the new transformation. So actually you'll see there's no changes there, because if you imagine that this axis is like a pole or a hinge and it's turned round, this graph is actually symmetrical. So now we're familiar with the rules and we're familiar what they do to graphs. We need to understand what's going to be asked of us in, say, the exam. In the exam you could be asked to draw the new graph, so sketch what happens to the graph, which is exactly what we've just done. Or you could be asked to rewrite a new equation. Or you could be asked to just sketch a graph which has clearly been transformed, and you need to recognize what rules are being used to do that. So we're going to go through a couple of examples now. So let's say the question asks, what transformations have been done to y equals x squared to get to the point of y equals x plus 3 all squared plus 1, for instance. And this is where our rules come in. So we start with our f of x equals x squared. To rewrite f of x equals x squared, because remember, everything comes from these core 3 graphs that we remembered at the start of this video. We need to know what steps are needed to get from here to here. Okay? So, first off, we always deal with the stuff inside the brackets here. So this f of x means whatever's inside the brackets here replaces x here. So here I have an x plus 3 all squared. So if I use the rule f of x plus 3, first, this means whatever is inside this bracket replaces this x here. So I get x plus 3 squared. I have a plus 1 here, so I need to add a 1 on the outside on both sides here. So you see, I've gone from here to here very quickly just by using transformation rules. And now I can describe what happens then. This rule here, as we know, is f of x plus a. So graph has been translated by vector, goes to the left by 3, and no change in the y-axis. Then it's been moved up by 1, because this is f of x plus a, isn't it? So then it's been translated, so followed by translated 0, 1 in the y-axis. So you see, we've sort of done 2 things there. We've rewritten the original equation, which was here, to match this one. We've described what's happened to it in words. And then I could very easily draw the graph. So this is my original graph here of f of x equals x squared. With my transformations, f of x plus 3 plus 1, the graph first from this bit moves to the left by 3, so that's minus 3, and then the last stage moves up by 1, so actually this is at minus 3 and this is at y equals 1. And you can easily find this intercept there because I can just put x equals 0 into my equation because y equals x plus 3 all squared plus 1. So at x equals 0, my y equals 3 squared plus 1 is 10.